All right, so like I said, I'm just going to go in order. So the first one I have here is page 267, number 6. Okay, so here I think we're going to have to look at it because we're looking at a graph. So it says, given the graph to the left, determine the following. So let's just kind of go through this real quickly here. So they want to know what f at 2 is. All right, so let's go here. We go at x equals 2, and we see that while it's approaching two different numbers left and right, the actual value at 2 looks like it's equal to 3. Okay, so it doesn't look like I'm going to write these down. I think we'll be able to just answer them. So the actual value, because there's a closed circle there, would be 3. Then we go to the limit as x approaches 2 from the left of f at x. So if I approach 2 from the left, the y values are approaching 1. They're approaching the y value where that hole is. Even though they don't reach there, remember, we don't care about that when we're talking about limits. Whereas here, they're asking for the limit as x approaches 2 from the right. So here we see that as we approach 2 from the right, the y values actually approach the function value of 3. So the limit as x approaches 2 to the right would be 3. And then number 4, it says, what is the limit of f at x as x approaches 6? Now you notice here, this is not a one-sided limit. So this is a true limit. So we have to be approaching from left and right, and there's only a limit if it's approaching the same real number. Okay? In this case here, whether I approach from the left or whether I approach from the right, I see the y values are approaching 2. Even though the function value is not equal to 2, we don't care about that. The only thing we care about is what it's approaching, and it's approaching 2 from both sides. So that means the limit does exist and it's equal to 2. Okay? Whereas they didn't ask us, but if we look at x approaching 2, this does not have a limit because it's approaching different numbers from either side. And then here it says, does the limit as x approaches 4 exist? Justify your answer. So if we look at x equals 4, well, we can even just take the left-handed limit, and right off the bat, we see that as x approaches 4 from the left, y approaches positive infinity. And of course, in order to have a limit, you have to be approaching a real number. So in fact, you don't even need to be checking the other side, although the other side, it approaches negative infinity. Okay, so answering this question here is all about understanding the difference between a limit, a left-handed limit, a right-handed limit, and understanding that what happens at the value we're approaching is not important. It's only what's happening as we're approaching that value, as we see, for example, as x approaches 6. Okay, any questions on this one here? Nope. Okay, so let's move on now to number 8. So here, I believe that's the next one. Oh no, 7, sorry, we're going to do 7. Okay, so in fact, I'll just change that to 7 there. And it gives us a function. Okay, so I'll write it out. So here it tells us that f at x is given by this function x squared plus 1, as is if x is less than 2, it's equal to 2x plus 1. When x is equal to 2, and it's equal to negative x plus 5 when x is greater than 2. Okay, so we notice here, and they want us to determine where f is discontinuous. Okay, that's what we're looking for. Okay, now for any number less than 2, this is just a polynomial function. So we know polynomial functions are continuous everywhere. So no need to worry about anything less than 2. For anything greater than 2, again, we have a polynomial function, so nothing to worry about. It's going to be continuous everywhere. The only place we have to worry is at x equals 2 because we have these changes. So remember that in order to be continuous, the limit has to exist and the limit has to be equal to the function value. Okay, so whichever you do first is not important, but let's calculate. I'll calculate the function value first. So f at 2, So for continuity, that does matter. We have 2 times 2 plus 1. So that's equal to 5. Okay. So now in terms of checking whether it has a limit, well, this is where we have to check the left and right-handed limits to see if they're going to be equal. And not only do they have to be equal, they have to be equal to the function value. Okay, so if I take the limit as x approaches 2 from the left, okay, so again, notice my notation here using the limit notation of f at x. Because I'm approaching from the left, I'm interested in this equation or this expression. So x squared plus 1. And here, again, I can just input the number because this is continuous function. So what do we have? We have 2 squared plus 1. And here we have 4 plus 1 is 5. Okay, so far so good. The left-handed limit is equal to the function value. Let's now check the right-handed limit. So limit as x approaches 2 from the right of f at x. Now I'm interested in the values just above 2. So here that's going to be negative x plus 5. And here, when I calculate that, what do I get? I get negative 2 plus 5 is equal to, and negative 2 plus 5 is 3. And we see that the limit does not exist. Okay, so since limit as x approaches 2 of f at x does not exist, f is not continuous at x equals 2. And that is the only place where it's not continuous, because we already made the argument that everywhere else we're dealing with continuous functions, and so they'll be fine. All right. So here, I suspect what you want to be looking at is how I actually wrote out the solution. And all I did is I just used the definition of continuity, that the limit has to exist and it has to be equal to the function value. So I have to deal with all of those components. All right, any questions? No, okay, so let's move on to the next one is 8b. Okay, so let's look at 8b here. So that's page 268. All right, so let's see what 8b has in store for us. So it says use algebraic methods to evaluate each limit if it exists. Okay, so this limit for b is the limit as x approaches 3 of x minus 3 over square root of x plus 6 and then minus 3. Okay, so ideally, if there's no issues, we can just stick whatever the x value we're approaching into the expression. But the problem is, I suspect that when we try to stick 3 into the denominator, we get 3 plus 6 is 9, square root of 9 is 3, minus 3 is 0. Okay, so that's a possible problem. So if the numerator does not approach 0, it's done. The limit doesn't exist. But we notice that the numerator also approaches 0. And so this is where we have to do, as we say, further investigation. Okay, and what we mean by further investigation is do some algebra to see if we can actually determine the value of this limit. All right, so remember, that's only the case that you have to do this if both numerator and denominator are approaching 0. Okay, now the problem, or the thing that's really causing the problem in terms of doing any kind of simplification, is this square root, as the x plus 6 is stuck inside that square root. So ideally, we want to get it out of the square root. And this is where we've seen this now many times, this idea of multiplying by the conjugate. Okay, so by now, it should be, your go-to when you see an expression with 2 terms, okay, and one of them or both of them have a square root. All right, so I'm going to multiply both top and bottom by the conjugate of that there. So it's going to be root of x plus 6 plus 3 over, and here, root of x plus 6 plus 3. All right, and we'll see where that takes us. So limit as x approaches 3. So you got to keep this down. We're not evaluating the limit yet. So you have to make sure you write the notation at every point. Now, I'm not going to multiply this out. And the reason is this, it's the denominator where I need stuff to happen. So I'm not going to do anything with the numerator yet. In fact, you should already have an idea of what you hope is going to cancel out at some point. Okay. So here, this produces a difference of squares. So it's like the first term squared. So it's going to be x plus 6 minus the second term squared. So that's going to be minus 9. And now let's see where this takes us. And here we have 6 minus 9 is -3. And lo and behold, we got to what we were hoping we were going to get to if this was going to work. Okay, this is another reason why I didn't multiply all this out, because I knew that the x minus 3, the thing that makes the expression 0, is what I should have been hoping was going to cancel out at some point. So now I can reduce this fraction, and now I'm left with something that I can just evaluate by inputting the x value there. So what do we have? Now I'm evaluating the limit, so I don't write the limit notation. So what do we have? 3 plus 6 plus 3. And this is 9. Square root of 9 is 3 plus 3 is 6. And there's the value of my limit. Okay. Now, by the way, one thing you can do as a check, you know, I wouldn't accept that at all as a solution to this problem, is, you know, you can stick some number very close to 3, say 2.999 into numerator and denominator, and that should give you something very close to what the answer would be. So you can use that as a check. Okay, but again, as I said, use algebraic methods. That's not enough of a solution. Okay, any questions here? Okay, so again, make sure you keep in mind that trick of multiplying by the conjugate. All right, so that was 8b. So now we are going to 26b. Okay, so if anybody came late, there were some questions that I announced that there was 1b was done in last week's tutorial, and the other ones that were asked for have videos for them already. So this is, what did I say, 26b? So that is going to be page 270. Number 26b. And what is this here? Use the algorithm for curve sketching to sketch the graph of each function. Oh, yuck. Okay, I was hoping not to have to do a sketching question, but we will. Now, one thing right off the bat I'm seeing here, let's write the function. Y equals 3x over x squared minus 4. Okay, and I'm going to do what I had suggested you do in this here. Is I'm not going to bother finding the first and second derivative, because as we saw, you know, likely these types of questions, they would be given to you. So I'm going to use good old Symbol Lab to do that work for me. Okay, so what I'm going to focus on here is the analysis of the function, the derivative, the second derivative, to get to a graph. So I'm going to try to fit it in what we have here. So I'm going to start now. I'm going to split it up into 3 parts. What is the information I can get from the function itself? Okay, so the domain here, well, it's going to be all real numbers, except the only thing that makes the denominator 0 would be 2 and -2. So I'm going to exclude 2 and -2. Okay, next I'm going to look for my x-intercept, which of course is what happens when the y is equal to 0. And since this is a fraction, in order for the fraction to be equal to 0, 3x has to be equal to 0, which means x has to be equal to 0. So there's my 1x intercept. Could go ahead and find my y-intercept, which of course is the value of y when x is equal to 0. And lo and behold, it's also 0, because I'm going to have 0 over -4. Okay. Now we'll go for our vertical asymptotes. Okay. Here we're looking for where the denominator is equal to 0. So x squared minus 4 is equal to 0. And so here we have x equals 2 and x equals -2. And I want to give it specifically like this because these are equations of lines. So those are my 2 vertical asymptotes. All right. So next we can go to the end behavior. Okay, and this is, we're lucky, a nice easy one. because the denominator has a higher degree than the numerator. Hence, we know that this is going to be approaching 0. So the limit as x approaches positive or negative infinity of my function is going to be equal to 0. So that means essentially that we have a horizontal asymptote of y equals 0. Okay. And lastly, I'm going to find the sign of the function. That can be useful sometimes in graphing. So here, the only place where this can change sign is at the x-intercept or at the vertical asymptotes. So here, -2, 0, and 2. So if I take -3, I see I have a negative in the numerator. -3 squared, 9 minus 4 is 5, so positive in the denominator. So negative here, if I take -1, we have again negative in the numerator, and 1 minus 4 is negative, so negative over negative, positive. Okay, and you see I do this relatively quickly. So let's take 1. Okay, positive in the numerator, 1 minus 4, negative. And then finally, if I take 3, well, it's going to be positive in the numerator, positive in the denominator. So there's my sign. Okay. So this is all the information we can get from the function itself. Now let's take a look at the derivative. And like I said, I'm going to use Symbolab. Does anybody want me to show using Symbolab here, just in case? I'm assuming, I hope everybody got familiar with it. No, okay, so I'm just gonna quickly stick it in there because I don't want to have to deal with silly mistakes. So derivative calculator. Okay, and in fact, I'm gonna use this for both the derivative and second derivative. So what do we have? It is 3x. Give me just a second. 3x over x squared minus 4. Okay. So it looks like what we have here is we have 3 times negative x squared minus 4 over x squared minus 4 squared. Okay. So now I'm looking for my critical points. Okay, so I already know where this doesn't exist. That's going to be a 2 at -2, but I know I already have vertical asymptotes there. So there won't be any extrema there. So I just need to determine when y prime is equal to 0. And that'll happen when negative x squared minus 4 is equal to 0. But here I notice if I bring this to the other side, x squared has to equal a negative number. That means there's no critical points because that's impossible. Okay, so there's no direct information in terms of maxima or minima here, but I can still determine when the function is increasing or decreasing because the sign of the first derivative is tells me the increasing and decreasing behavior. So here, the only 2 places it can change sign is at -2 and 2. But now that I look at this, this is very interesting because we have 3 is always positive. X squared minus 4 squared is always positive. And look at the denominator. I've got some negative number -4, which is always negative. So I don't really have to do any work here. This thing's always going to be decreasing. Okay. So in the end, didn't get too much information from the first derivative. So let's see what we can get from the second derivative. And again, I'm going to use Symbolab and a little trick. I mean, you can't see me doing this here, but I already have d over dx of 3x over x squared minus 4. I'm just going to put a little exponent 2 because we know that that's the on both the d and the dx because that's the notation for second derivative. And I'm just going to go straight and now find the second derivative. Okay, so that is negative 6x times negative x squared minus 12 all over x squared minus 4 cubed. Okay, that would have been a real mess to determine on our own. This wouldn't have been so bad. This would have been quite a bit of work. All right. So now I need to determine when the second derivative is equal to 0. So that's going to happen when negative 6x is equal to 0 or negative x squared minus 12 is equal to 0. So here we have x equals 0. Okay, it's pretty obvious. But here, hey, we got something similar to before. Negative 12 is equal to x squared. This is impossible. So no solution from this part. So our only possible point of inflection is at x equals 0. So now I will find the sign of the second derivative. Of course, I'm still going to include negative 2 and 2 because the sign of the second derivative also gives me the concavity. All right. So here, let's pick, I don't know, negative 3. So what do we have here? Negative 6 times negative 3 is positive. Notice this thing is always negative, like before. So negative times negative is positive, times negative is negative. And then here, this is like 9 minus 4, 5. So this is going to be positive. So it looks going to be negative here. Let's take negative 1. Okay, again, negative times negative times negative, negative over 1 minus 4. Negative cubed is still negative, so positive. Okay. Then pick 1. So negative, positive, negative, positive over. This is 1 minus 4. Negative cubed is negative, so negative. And let's do last one here. Let's pick 3. This is negative, positive, negative. Okay. And here 9 minus 4 positive cubed is positive. Okay. So that means now I have a point of inflection because the sign changes at 0, but we already know that at 0, the y value is equal to 0. All right. So this is all the information we can get. And so now I'm going to draw my graph and I'll just draw it by hand here. Okay. So let's see what we got. So the numbers are pretty small. So here we'll go 1, 2, negative 1, negative 2. Okay, I never really have to deal with the only y values I think I have to deal with is 0. So I'll just put 1 there just to say that I have a scale. Okay, and let's see what happens here. I've got my vertical asymptote, my other vertical asymptote, and the only point of interest is at 0, 0, which is both the x-intercept and the point of inflection. Okay, so let's start drawing and I go from left to right. So if I look to the left of 2, I know the function is negative, I know it's decreasing, and I know it's concave down. Okay, now since the end behavior approaches 0, must be approaching from the bottom, and I know it has to be approaching the vertical asymptote, so it has to look something like this in order to fit all those parts. Okay. So next, from negative 2 to 0, the function is positive, still decreasing, but now the concavity is upward. And again, I've got this vertical asymptote, so I must be doing something like this, and we have a point of inflection. So that means it should be changing concavity. So now it's going to be concave down. It's going to be negative, but still decreasing. So it's going to have to be something like this. And then lastly, it's positive, still decreasing, but concave up. And I've got the vertical asymptote and the end behavior approaching 0. So it must look something like this. And there's my graph. Okay. So this really is about just following the algorithm and being able to interpret what the algorithm tells you. Okay. In some ways, there's kind of very little thinking here. You just want to interpret exactly the information that you got. Any questions on this here?
Yeah, Tony, I have a quick question.
Yep.
So what would he have to like, you'll be probably just give us a derivative. for the functions.
Unless
correct?
it's a very easy, like let's say it was a polynomial, no, I wouldn't.
Okay.
But most likely anything that involves something that would involve a product rule, chain rule, quotient rule, yes, you would very likely just get the derivative and second derivative.
Okay, thank you.
Okay, anything else? All right, so let's move on. So I think there was one more in this section, number 29. So this is going to be page 270, number 29. All right, so let's see what we got here. So this has, okay, research laboratory, bacteria infected with particular disease, the equation. Okay, so we have this equation, N of D is equal to 15D times E to the negative D over 5. Okay, models the number of bacteria that will be infected after D days. Okay, so part A asks, how many days will pass before the maximum number of bacteria will be infected? Okay, so essentially what they're asking us is, where is the location of the maximum? Okay, because D is like our X value. So they essentially want to know what is the X value of the maximum of this function. Okay, so now I'll just go through my algorithm for determining maximum and minimum. Okay, now here they don't specifically tell us, but obviously we're assuming that D is greater than or equal to 0 because the, it actually needed to be administered in order for us to be doing this experiment. So I'm going to find the derivative to hopefully find my critical points. Now here, this 15 is just a constant. So I'm just going to take it out and not worry about it, since it's just a constant multiplying this function. So now I'm going to use the product rule on this function here. Okay, so again, just follow my rule here. Derivative of the first is going to be 1. And then here times the second function, e to the negative d over 5. Okay, and then plus my first function, which is d, times the derivative of the second function. Okay, so this is an exponential function. So think of it as e to the u. What's the derivative of e to the u? Just e to the u. But now I need to multiply that by the derivative of u. So what's the derivative of negative d over 5? Well, it's like negative 1/5 d. Derivative of d is 1. So it's just negative 1 over 5. Okay, lots of brackets there. Okay, and of course, what we want to do is determine when that derivative is equal to 0. Okay, so here I've got my 15. And I notice, again, this is a good trick that you always want to keep in mind. I notice that there's a common factor between the first two terms. So I'm going to take out that e to the negative d over 5. And what are we left with here? Well, here we're just left with 1 and then minus the d and the negative 1 over 5. So the minus because of that subtraction. So minus d over 5. Okay. So we need to solve this equal to 0. Okay. This never equal to 0 because it's an exponential expression. So I don't have to worry about that. So the only thing I got to work with is that 1 minus d over 5 when that is equal to 0. But what do we have? We have d over 5 is equal to 1. So d is equal to 5. Okay. Now, again, we can't be guaranteed that this is our answer. Okay. Because we have to check that this is indeed a maximum. Okay. So this is where I'm going to use my number line here. Okay. Now, in fact, I'm not going to use a full number line because really I'm only starting from 0. I don't care about anything less than 0. Okay, so my only critical point is at 5. So let's check, 1 here. And what do we have? Well, this is positive. This is always positive. Again, exponential expression. So 1 minus 1 over 5 is going to be a positive number. Whereas if I put something like 6, 1 minus 6 over 5 is going to be negative. Okay. So we see that from 0 to 5, it's increasing. And then afterwards, it's continually decreasing. So it is indeed a maximum. Okay. So the answer for A is, what did they ask again? After how many days will pass? So this will be after 5 days. Now let's see what B asks us. Determine the maximum number of bacteria that will be infected. Okay, well, this is where you just take the time at which you have your maximum and stick it into your original function. So essentially we're looking for n at 5. So what does that give us? 15 times d, which is 5, times e to the negative, 5 over 5. So e to the negative 1. Now, obviously, I'm not, so this is 15 times 5, 75, and e to the negative 1 is like 1 over e. We don't want to leave our answer like that because there's a context we should be giving an answer here. So let's get our calculator and calculate 75 divided by 2.718. And that's 25.6, sorry, 27.6. Okay, and obviously you can't have 0.6 of a bacteria. So here, now this is where normally you would, I guess normally you would go up to 28, but here the bacteria has to actually be infected. So it looks like 27 will be infected. It looks like you're never going to get to 28. So here, 27 bacteria. It is bacteria, right? Yeah. Okay. So again, here, it was just interpreting that despite the fact that we had this context, essentially we were just looking for a maximum value. And so we used our calculus procedures and checks to show that we would have a maximum here and then determine the value. All right, any questions on this one? Nope. Okay, so we're going to move on to, I believe there was one question from the logarithm stuff. Yeah, page 575, number 9A. Page 575, number 9A. All right, so let's see what that looks like. 575. All right, so it gives us a function. So f at x, let me just write that down. F at x is equal to x ln x all squared, x ln x all squared. And it wants us to determine all the points at which the graph of f at x has a horizontal tangent line. Okay, so again, we interpret that horizontal tangent line means the slope has to be 0. Hence, the derivative has to be 0. So it looks like they're just asking us to determine when the slope of this, or when the derivative of this function is equal to 0. Okay, so let's start by finding the derivative. So f prime at x. So here, I'm going to use the chain rule, but of course, I can see already I'm going to have to use more than the chain rule. So here, what's the derivative of u squared is just 2u. So 2 times x ln x. And then the chain rule tells me to multiply that by the derivative of that inside function. Okay. And the derivative of that inside function, I'm going to have to use the product rule. Okay. So the derivative of x is 1 times the second function, ln x, plus the first function, x, times the derivative of the second function, which is 1 over x. Okay. And now I want to determine when this is equal to 0. Okay. So let's clean this up a bit. So we got 2x ln x, and then here, these just cancel out. So we've just got ln x plus 1. Okay, and what's really nice about what we have is it's already in factored form. Okay, so no other work to do. So if I look at this here, I see that x can be equal to 0, ln x can be equal to 0, or ln x plus 1 can be equal to 0. Now, while this looks like a good candidate, of course, ln x is not defined at 0. So this is not part of the domain. So 0 not in the domain of my function. So that's gone. Okay. So here you could just remember that, logarithmic functions are equal to 0 when the input is 1, or if you use opposite inverse functions here, x is just going to be equal to e to the 0, because that's the opposite function to, or the inverse function of ln x, which of course is equal to 1. So whether you just remember this outright or you use inverse functions, you get to the same answer. Okay, so there's one of my answers. And here, so ln x is equal to -1. So here again, you know, this is e to the -1 equals x. So x is equal to e to the -1 or 1 over e. All right. So these are the x values. And already I don't remember if that's what they were asking for or if they were asking for more. So I'm going to go back and check my question. And it says determine all the points at which the graph has a horizontal tangent. So I do need to find the y values. So here, y is equal to 1 times ln1 squared. But of course, ln of 1, as we just talked about, is equal to 0. So this whole thing is equal to 0. Okay, so 1, 0 is one of those points. And here, let's stick this into my expression. So what do we have? We have 1 over e ln of. Now, because I have ln, I'm actually going to put this in as e to the -1, okay, which is equivalent to 1 over e. And the reason why I do that is I notice, natural logarithm and the function e to the x are, oops, this is squared, are inverses of each other. So that just gives me a final result of -1. So this is -1 over e squared, which of course the negative disappears when I square it. So my second point is going to be 1 over e squared. Okay. So in some ways, finding the y values was almost more work than finding the x values here. But if we go back to the main idea here, is that we want to know when the tangent is horizontal. In other words, we need to determine when the derivative is 0. And we have to apply not only our derivative rules, but do a little bit of algebra. All right. Any questions on this one here? No. Okay. So now we're going to move to the vectors stuff. All right. So this is 557. All right. So I'm going to try to go in order here. So number 7. So page 557, number 7. Okay, so this says determine the coordinates of the unit vector. Okay, so right off the bat, I'm thinking magnitude of 1 that is perpendicular to these two vectors. So I'll write those down. We have A, which is 1, -1, 1, and B, and you shouldn't be surprised that I'm writing them one over the other because I'm seeing where this is going, 2, -2, 3. 2, -2, 3. And the reason why I wrote them one on top of the other is because they're asking me for a vector that's perpendicular to both of these vectors. Hence, I know that I'm going to be taking the cross product of those two vectors. So if you use my method, this is how you'd be setting it up. If you use some other methods, set it up however you do it. Okay, so here, let's put my 1 and my 2. And again, please keep track of my algebra, my arithmetic here. So A cross B. So we're going to hide that. So what do we have? We have -3 minus -2. So -3 plus 2, -1. Here, hide that. We have 2 minus 3 is again -1. And then here we hide those. And we have -2 minus -2. So -2 plus 2 is 4. Okay. But all we found here is a vector that's perpendicular to those two vectors. We're looking for a unit vector in that direction. Okay, so this is where we're going to remember how we find unit vectors. You just take the vector, in this case here, -1, -1, 4, and you divide it by its magnitude. Okay, so 1 squared is 1, plus 1 squared is 1, plus 4 squared is 16. So here we have -1, -1, 4. over square root of, let's look like this, is 16, 17, 18. Okay, so here we have -1 over root 18, -1 over root 18, and 4 over root 18. Okay, I think it's 0, not 4. Oh, crap. Which one is this? Oh, for here? So -2, oh, +2. Yeah, that was 0. Yeah, thank you, thank you. Okay, sorry about that. So here, this is just going to make it a little, sorry, it's going to be a little messy. So that's just going to be +0. So this is just going to be, it looks like it's going to be root 2. Okay, so luckily, not too bad. Just a little ugly. I'll rewrite it here. So it's going to be -1 over root 2, -1, oh, and that's 0. So -1 over root 2, and that will be 0. Okay, sorry about that. So that should fix it. Okay, so again, as soon as you hear a vector perpendicular to two other vectors, you should be thinking take the cross product, and anytime you're hearing unit vector, you should be thinking of taking your vector and dividing it by its magnitude. All right, any questions on this one here? No, okay, let's move on. All right, so the next one I have 7, I guess would be 10. Okay, so that's going to be on the same page. Page 557, number 10. Okay, so this is determine a vector and parametric equation for the line that passes through 0, 0, 4. Okay, so that's good because we need a point to get the equation of a line, and is parallel to the line with the following parametric equation. So it's parallel to this one here. So x equals 1, y equals 2 plus t, and z is equal to, where is it? Oh, -3 plus t. Okay. Now, since the only use for this line here is that it's parallel to the line we're looking for, the only thing I really care about for this line is its direction vector, because if the two lines are parallel, then we can use the same direction vector to define them. So what is the direction vector here? Well, there's no t term, so that means it's like 0t. Here we have 1, and here we have again 1. Okay, so what we have here is a line that passes through 0, 0, 4 and has a direction vector of 0, 1, 0. So I can give its vector equation as 0, 0, 4 plus, I won't use t since it was also used, so I'll use s times 0, 1, 1, where s can be any real number, and then we can write it in parametric form. So x is equal to, well, 0 plus 0s, so x is just equal to 0. Oh, somebody asked how I got 0, 1, 1, so let's just take a look. So remember what I'm looking at. The line I'm looking for is parallel to this line here. So that means if I've got these two lines that are parallel, if whatever the direction vector is to one line can also be used as the direction vector to the other line. Okay, so I was looking for the direction vector of this line, which is given by the coefficients of t. Okay, here though there is no t term, so it's like having plus 0t, so that's where I got the 0. Here the coefficient of t is 1, coefficient of t again is 1, so this is my direction vector, which can also be used for the line I'm looking for. Okay, does that answer the question? Okay, great. What was I doing? Oh yeah, parametric form. So 0 plus 0s. So x is just always equal to 0. Y is given by 0 plus 1s. And then z is given by 4 plus 1s. And again, s is any real number. Okay. So again, it's about understanding, how I can use the information given to help me get information about the thing I'm looking for. Okay, any other questions on this here? No, okay, let's move on. All right, we are now going to, looks like number 15. Number 15, so this is page 558. Page 558, number 15, okay. So let's see what this one is asking. It says, determine the equation of the line that passes through the point 102. We have the point, so here we're looking for a line. So passes through 102. And intersects this other line at a right angle. Oh, okay. So it intersects the other line, which is, let me just write it out here, -234 plus s times 112. Okay, at 90 degrees. Okay. So I'm looking for a line that contains some point, okay, and has to be perpendicular to some other line, okay? But the thing is that like there's lots of lines that are perpendicular to that line there. So it can really go in any direction, okay? Even if it's, even if they intersect at a right angle, can you see that there's lots and lots of lines that intersect this line at a right angle, okay? We need to find the one that passes specifically through this point, okay? So this is a bit of a tougher question, okay? I'm suspecting, because it's not the usual kind of information that's given. And so this is where, as I keep suggesting over and over again, if you get something that's a little tougher, is really try to use a diagram to lead you here, okay? So what I've got is I've got this line here, okay? And I've got the line I'm looking for, which intersects it at a right angle, okay? The line I'm looking for contains the point 102. And the line I'm given, well, since these two things have to be perpendicular, okay, what I know for sure is that their direction vectors are also going to have to be perpendicular. So I suspect that's the key to solving this problem. And of course, we know, how do you find the angle between two lines? Well, you look at their two direction vectors. So given that we've done that in the past, it makes sense to work with this here. So I know that this direction vector, which is 112, has to be perpendicular to the direction vector of this line. The problem is I have no clue what the direction vector is of this line, okay? But let's try to create one, because what did they tell us about these two lines? They're not skew, okay? They're not parallel. They intersect at a right angle. So I don't know what this point is here, but I know if I join the point of intersection with that point there, it's going to give me a vector that is parallel to the line I'm interested in, and hence perpendicular to that one. And this, what I'm going to show you now, is really the trick to solving this problem. So this is a bit of a tougher problem. That's good. It's good to work on some tougher ones. Probably not something you'd expect on a final evaluation, but okay. What I know is that this point is on the given line. That means this point, okay, can be written using this equation for some s value. So the x component of this point can be written as -2 plus 1s, okay? the y value can be written as 3 plus 1s. Okay, and the z component can be written as 4 plus 2s. Okay. Okay, so just want to make sure you're seeing what I'm doing here is because this intersection point is on the line that's given, it can be written in this form. But look what I can do now. I can join this with the point that I know on the line. Okay. Now, this is where I'm gonna, we've used this trick before, is you see the way I've drawn the vector from here to there, which means my subtraction would have to go like 1 minus -2 plus s, blah, blah, blah. I'm just gonna make my life a little easier and make the vector in that direction, which is perfectly fine, right? Because it doesn't matter. It has to be anything parallel to this line. It's just gonna make my algebra a little easier. So let me call this M. So M is going to be gotten by subtracting, second minus first. So it's going to be -2 plus s minus 1. So -2 minus 1 is -3. So this is just going to be s minus 3. Here, 3 plus s minus 0. So I'll just write it as s plus 3. It's nice to have the variable in front. And then lastly, 4 minus 2s minus 2. So 4 minus 2 is 2. So it's going to be 2s plus 2. So this vector here, okay, which is going to be the direction vector to the line, has this form, okay? But what do we know about this direction vector and that direction vector? They have to be perpendicular. Hence, s minus 3, s plus 3, 2s plus 2, dotted with 1, 1, 2, has to be equal to 0. And I think we're going to end up with something that we can now solve, because now we can take the dot product 1 times s minus 3, okay, plus 1 times s plus 3, okay, plus 2 times 2s plus 2. And look what we have, an equation that only has s's. So s plus 4s, so that's 6s equals -3 plus 3. That goes. So what are we left with? We're left with 4. So if we bring that to the other side, -4, I was hoping this was going to be an integer, but so 4 over 6 is 2/3. Okay, so now I can stick this into here to find the direction vector for my line. Okay, so let's see what we get. We get m is equal to, so here, I'll write it out, -2 over 3 minus 3. But instead of writing -3, I'm going to write -9 over 3. So they have the same denominator. So here, s plus 3, -2 over 3 plus 9 over 3. Here I have 2 times -2/3. Okay, it's going to be again over 3, so plus 2, so plus 6 over 3. So what do we have here? We've got -2 minus 9, -11 over 3. Okay, here we have -2 plus 9, so it'll be 7 over 3. And here we have -4 plus 6, 2 over 3. And here I can now write the equation of my line. Passes through 1, 0, 2, plus, I won't use s again, I'll use t this time, because we already used s over there, -11 over 3, 7 over 3, 2 over 3. Okay. Now, you could simplify this a bit, because do you have to use this vector here? No, you could use any vector parallel to that line. So you could have also just multiplied this by 3 and used -11, 7, 2. That would have also been acceptable. In fact, would have been a little nicer when you think about it. Okay. So again, like I said, this is a bit of a tougher problem, but I kind of used all the, all the stuff that we'd seen in terms of working with equations of lines and finding direction vectors, but I had to be a little clever here in working with this point of intersection, even though I didn't know what it was. Okay, so nice problem. Like I said, probably a little more complex than one should expect on an exam or final evaluation. All right, any questions on this here? No, okay, let's move on. So 15, next we're going to 17D. So this is going to be still on page 558, page 558, number 17D. Okay, so let's see what that asks. So it's determine a Cartesian equation for each of the following planes. Okay, so here it's going to be through the points. They give us 2 points. So 3, 1, -2, 3, 1, -2, and let's see the other one here. 1, 3, -1. And it has to be parallel to the y-axis. Okay. All right. So here again, we have our plane, and remember what we need. Okay. Eventually we need to find a normal vector since they want the Cartesian equation, but I'm pretty sure we're going to have to do that by getting two direction vectors. Okay. So we already know that one direction vector can be found by connecting these 2 points. Okay. So one direction vector, since these 2 points are on the plane, we can just connect these two. Okay, so if I use AB, you could use BA, doesn't matter. So AB, so 1 minus 3 is -2. 3 minus 1 is 2. And then -1 minus -2, so -1 plus 2, looks like that's going to be 1. Again, make sure you're checking my algebra here. Okay, now how to get the second direction vector? Well, actually, it's going to be a little easier because remember what you have here is this plane is parallel to the y-axis. Okay, so that means any vector along the y-axis, which is just going to be a line. Okay, y-axis just represents a line. So any direction vector of that line can also be used as a direction vector for your, maybe this is a nicer way of showing it. So if this plane and the y-axis are parallel, any vector on the y-axis will also be parallel to the plane. And of course, what is the easiest vector that's parallel to the y-axis is 0, 1, 0. Okay, and this is going to be our second direction vector. Okay, so now that we have A and B, we can take their cross product to find the normal vector. So -2, 0. Let me try to do this one without an error. Okay, so what do we have? We have 0 minus 1 is -1. Okay, here we have 0 minus 0 is 0. And here we have -2 minus 0 is -2. Okay, so there's my normal vector. But because I know that I would like my leading coefficient to be positive, I'm actually going to use this as my normal vector, 1, 0, 2 multiplied by -1. Okay, so now that I have my normal vector, I've got 2 points. Pick the one you like, and I'm going to stick this into my equation AX plus BY plus CZ plus D equals 0 or equals D, doesn't matter. Okay, either way. So here we have A is 1 times, I'll use that one there, 1 plus B is 0 times 3 plus C is 2 times -1 plus D equals 0. So here, what do we have? We have 1 minus 2 is -1. Bring that to the other side. D is equal to 1. So my final answer is going to be 1 times X plus 0 times Y plus 2 times Z plus 1 is equal to 0. Okay, and there's the equation of my plane. Okay, so again, given 2 points, you can create one direction vector. And because you know that the plane is parallel to this line, any direction vector of the line can be used as your second direction vector. Okay, any questions on this one here? No, all right, let's move on. Okay, next we have number 20. So that is, again, page 558. 558, number 20. Let's see what that looks like. So a line with equation blah, blah, blah intersects the plane at an angle of theta degrees. Determine this angle to the nearest degree. Okay, so let me write everything. So there's three parts here. So R is 1, 0, -2 plus S 2, -1, 2. And of course, S can be any real number. I won't write that out, but make sure you do when you're giving an answer. And it intersects the plane. So X plus 2y plus Z, X plus 2y plus Z equals 2. Okay, at theta degrees. Okay, determine theta. So this is one of these where we've worked with angles between things. I'm not sure that we've worked necessarily with an angle between a line and a plane. So this is where, again, as soon as it's something a little different, where it's not obvious how to go ahead, I'm going to draw myself a diagram here to hopefully help me out. Okay, so I've got my plane. Okay, and I've got this line that intersects it. And so here, what I want to do is I want to find the angle between the line and the plane. So imagine, this is, my line and my plane. I want to determine this angle here. But of course, anytime you're working with the Cartesian equation of a plane, you presumably want to incorporate the normal. Okay. So what I'm also going to include here is the normal vector, which of course is perpendicular to that plane. And this is where I realize, well, even though I'm looking for the angle theta, hey, look at that. It's complementary to the angle to the normal. Okay, I mean, I don't know how good it'll look here, but if I, there's my line. Okay, there's my normal. So the angle to the plane and the angle to the normal make up the 90 degree. So again, I'm going to do this indirectly. I'm going to find the angle to the normal and then subtract that from 90 in order to get the angle I'm looking for. Okay. So if I want to get so there's my direction vector. So I'm going to find the angle between the direction vector and the normal vector. So let's start with that. So n dot m, of course, we know is the magnitude of n times the magnitude of m times cosine of the angle between them. Although here I'm going to use phi because that's what I called it there. So now what is n? It's 1, 2, 1. M is 2, -1, 2 is equal to, what is the magnitude of n? So square root of 1 plus 4 is 5 plus 1 is 6. So square root of 6 times, let's find the magnitude this here. 2 squared is 4 plus 4 is 8 plus -1 squared is 1, 9. So that'll just be 3 times cosine of phi. Okay, so phi is going to be equal to cos inverse of, so let's do this here. It's 2 minus 2 plus 2 over 3 square root of 6. Okay, and let's see what we get. So this is just going to be, those cancel out, so it's going to be 2 over that. Okay, so let's check this out here. So we have cos inverse of 2 divided by 3 times square root of 6. So 74.2. Okay, but remember, we're not looking for 74.2. We're looking for theta, which is 90 minus 74.2, which is 15.8. Okay, and there you go. So again, bit of a different question, but again, with the diagram, we were able to figure it out. So let's look at, I think there were some other parts here. So what does B ask? It says show that the planes, blah, 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 are perpendicular. So here, plane 1 is 2x minus 3y plus 2z, 2x minus 3y plus 2z is equal to, oh, it's minus 1 equals 0. So I just put equals 1 there just so I don't have to rewrite it. Plane 2 is 4x plus 3y minus 17z, 4x minus 3y, whoops, minus 17z is equal to 0. And we want to show that these two things are perpendicular. Actually, this is a much easier problem than A, because we know that to show that two planes are perpendicular, their normal vectors are going to have to be perpendicular. Okay, so I'm just going to take the dot product of the first normal with the second normal and hopefully show that that's equal to 0. So what is the first normal? It's 2, negative 3, 2. And I'm going to dot that with 4, negative 3, negative 17. And let's see what we get here. 2 times 4 is 8, plus 9, minus 2 times 17. Oh, that's not going to give us, it's not going to give us 0. So I'm surprised. Oh, come on, people. I asked you to be on the ball here. This isn't 2z, it's z. So that means this is going to be 1. Okay, so minus 17, there we go. That's equal to 0. Okay, so therefore, plane 1 is perpendicular to plane 2. Okay, let's take a look at B. So, oh, sorry, C. We did B already. So C here, show that the planes are parallel and not coincident. So that should be pretty easy because we've got 2x minus 3y plus 2z minus 1 equals 0. And here we have 2x minus 3y plus 2z minus 3 equals 0. So here we have that n1 is equal to n2 because the two normals are exactly the same. They're not even scalar multiples. They're exactly the same. Okay, but we see the d values are not equal. Okay, so therefore parallel, but this means distinct. Okay. Any questions on this here? Okay, again, if you get stuck, even with an easier question, don't hesitate to draw yourself a little diagram. Okay, so let's see if there's any chance of my finishing. There's one problem left, which is number 21. It says two forces, 25 and 40 newtons, have an angle of 60 degrees between them. Determine the resultant and the equivalent of these two forces. Okay, yeah, that should be fairly straightforward. So here, page, again, 558, number 21. So here, let's draw the vectors. We've got 40 and 25. So 40 and 25. So again, we're looking for the resultant. So that means we're adding them together. So here, if this is 60, this must be 120. And so this is 40 and 25. So the resultant here, okay, we're going to use the cosine law. So it's the square root of 40 squared plus 25 squared minus 2 times 40 times 25 times the cosine of the angle between them, which again, of course, do not forget is not the same as the angle. Sorry, it's not the angle between them, but the angle opposite to the length. Okay, so let's calculate this here. Square root of 40 squared plus 25 squared minus 2 times 40 times 25 times cos of 120 is 56.8. Okay, so this is going to be the magnitude of the resultant, but also the magnitude of the equilibrant, because we know that that's just going to be in the opposite direction, but same magnitude. But now we want to find the direction. So when I look here, as I already have this set up with the resultant, and I see that in the same triangle that I just solved, I can find this angle theta, which will be the angle between the 40 Newton vector and the resultant. Okay, so this is what I'm going to use to describe my direction. Okay, so as I've said many times here, when I've only got one angle, yes, technically it is an obtuse angle, so I don't have to worry about the ambiguous case, but it's just to get myself used to, just using cosine law, so as not to have to worry about that case at all. So if I'm looking for theta, that's going to be cos inverse of, okay, so its opposite side length is going to be the 25. So that's the one that's going to come first, 25 squared minus the square of the other two sides. So 40 squared minus 56.8 squared, all over -2 times 40 times 56.8. Okay, so let's get that angle there. So that's going to be cos inverse of numerators 25 squared minus 40 squared minus 56.8 squared. Okay, close my bracket, divided by, open up my bracket, -2 times 40 times 56.8. Okay, so it looks like I got 22.4. Okay, so to describe my resultant vector, I'm going to say it's 56.8 newtons, and then it's 22.4 degrees from the, and just to make my life easier, let me call this U and this V. Okay, so from U toward V. Okay, and now if I'm looking for the equilibrant vector, well, I'm going to start from U, except I'm going to use that angle there. Okay, and of course that angle is just 180 minus the one we found, so 157.6. So that's 157.6. Okay, so my equilibrant vector is going to be again 56.8 newtons, and it's going to be 157.6 degrees from U. And now I'm going to say I'm moving away from V. And there is my answer for both. Okay, any questions on this here? So again, just set it up that the addition was careful with my angles and used relative directions in order to describe the directions of those two vectors. All right, any questions here? Okay, so what I'm going to do is I'm just going to stop the
Oh, Tony,
thing.
I'm so sorry.
Yeah, hold on a second. Hold on.
Yep.
Yeah, sorry, is there a mistake?
No, there's no mistake. It was just a quick question about like conceptuality regarding the equilibrium.
Yeah.
So what the equilibrium is, it's essentially the magnitude is going to be opposite. It's just the angle in this case will have to be, for this situation, just 180 minus what we got, correct?
Yeah, hold on. I pressed the wrong button here. Is this still recording? Yes, I pressed the wrong button. There you go. Stop recording.